Okay, let's carry on. So I want to talk about a particular case study in Hong Kong, but before we do that, I want to show you some details of land reclamation in Hong Kong, because it seems to be the hot topic these days. Not just in Hong Kong, in coastal cities, we try to reclaim the land back from the sea. Singapore, in Europe, could be the Netherlands, Japan, coastal cities in mainland China as well. We see a lot of reclamation activity happening. Now, since this topic is on deep replacement, we will talk about stone columns. The word stone is, of course, not something we're used to as geotechnical engineers, because we often like to use very well-defined soil classification systems, such as the British Standard or USCX. Stones in this case could mean gravel, could mean cobbles, and to a lesser extent, I don't think it means sand, but we're generally talking about coarse-grained fill material. So before we jump into the use of stone columns and particularly focus on the Penny Bay reclamation, I want to discuss the use of different types of reclamation. In Hong Kong in the past, we tend to carry out something called Foley dredge reclamation. What that means is Foley dredge reclamation. So what this means is, in the past, we had the luxury to scrape up all of the clay. So let's say this is the sea. We have, let's say, a layer of marine deposits. Underneath, we have some alluvium or CDG underlain by some maybe rock material. In early stages of Hong Kong's development, particularly for reclamation, we did have the luxury to carry out dredging. Now, what's dredging? Dredging would be, we use machines to take away this MD layer. It's very effective if you take away the MD layer, because you don't have residual settlement issues. The only thing you have to worry about after you remove the MD layer is, well, you need to replace it with sand, right? You can have some sort of ship here with some sort of gate underneath, and you can rain sand down onto this alluvium CDG layer. We don't expect the aluminum CDG layer to consolidate too much. You can also have what we call rainbowing. So let's say there's we have some sand here. So we can also take sand from one location, and we can use ships to rainbow it down in another location. Right? So in the past, we could use these kind of techniques. Sand, we call this sand mining, essentially taking sands from coastal areas and raining it in another area. But there are a few disadvantages of doing this. Number one, I think sand mining is known to be quite destructive to the ecosystem on the seabed, number one. So that's not that great, but minus the sand problem, with marine deposits, when you dredge it, the problem is, where do you place the marine deposits? In Hong Kong, we have something called, I think they're called marine MD, waste mud pits, I think they're called. So there are a few locations in Hong Kong, and these are in the open sea areas where they have formed some pits. So if this is the sea, we have some designated areas where we have formed some pits in the sea, where we can actually dump dredged marine deposits, and then we can eventually probably seal it, right? So if you type on Google, you look at waste mud disposal sites, you'll notice there are a few locations in Hong Kong, but the problem with these locations is eventually there's a finite volume with these mud pits. You can't continuously dredge mud, put them in the pit and expect to have an infinite disposal site. So over recent decades, you've noticed that we've tried to shy away from dredge type or fully dredged reclamation. Number one, what are you going to do with the mud? More often than not, the mud is actually contaminated through other various environmental processes. So it's not environmentally responsible to just dump it wherever you want. So you have to bring it to these designated waste mud pits and place it inside. And there's actually a cost associated with the amount of mud you dispose these pits per cubic meter. So that's one of the disadvantages of fully dredged reclamations. Other disadvantages are quite obvious. When you remove this green layer here, you lose a lot of volume. And when you lose volume, as we mentioned several times in our course, you have to replace this volume. And more often than not, it's sand, right? Not to mention dredging takes time as well. Some special cases, for example, for a third runway system for the Hong Kong International Airport, the third runway actually was constructed over a few contaminated mud pits, meaning that the mud, was contaminated, and it was in the best interest not to disturb these mud pits because we could release various types of pollutants into the seawater. So we'll talk about it later on. Eventually it was decided to use deep cement mixing for those cases. So this is what we would call a fully dredged reclamation. Now, with a fully dredged reclamation, let's see if I can complete this. With the fully dredged reclamation, well, with any reclamation, there's two components. Normally, before we carry out any reclamation, we try to construct some sort of we call this a seawall, for example, okay? And we construct seawalls surrounding our entire reclaimed block of land. Why is that? Well, we need to contain our reclamation and protect it from the ocean, essentially. So we normally construct a seawall, and if it's a fully dredged reclamation, you would even, let's say there's a layer of MD here, you would even remove this MD here and have the seawall, which can consist of fill material, fill. You have a seawall here. You place your fill material directly on alluvium or CTG lake, so you don't have to deal with settlement of the seawall. Now, this would be a fully dredged reclamation. Now, fully dredged also means we have to remove anything inside here, and then we, of course, fill all of this up with sand or some sort of fill material. Now, the question is, will this sand settle? Yes, it'll also consolidate to some degree, but the time required to consolidate fill material is much shorter than that of marine deposits with a much lower permeability. You can guess there might be some settlement, but it's not a big deal. Just replace it with more fill material. So what you see described here is what we call fully dredged reclamation. My drawings are much worse than what's shown on the slide on the top of the corner, but that's what we call a fully dredged reclamation. Now, with time, we realized, as I mentioned, that it's not sustainable to carry out fully dredged reclamation, right? So we start to look at, can we carry out partially dredged reclamations or undredged reclamations? Now, when you start carrying out partially or undredged reclamations, this is where the challenge comes in, because you now have to deal with the highly compressible clay layer. So if we look at, well, we can say partially dredged. So a partially dredged reclamation may look something like, see, we have an MD layer. Under the MD layer, we have alluvium or CDG. So a partially dredged layer means we could, let's say we want to build a seawall. We can build the seawall something like this. So to build the seawall, we can remove the MD layer first and then build this blue seawall on top of it. So the blue part is the seawall. So once you build a seawall on dredged, where you dredge the MD away, then you have a pretty solid underlying geological strata, right? If you have aluminum or CDG, so you're not quite worried about the failure of the seawall. We'll talk about later on when you do a fully non-dredged reclamation, where you might be concerned about the stability of the seawall. Bear in mind, the seawall is quite unique in that when you start filling the area behind the seawall, it has to be able to take all that earth pressure. Now, why do we call it partial? Well, in this case, we've removed the MD layer just for the seawall, but we can keep the MD layer inside the reclaimed area. In that case, what can we do? Well, we can perhaps install some PVD drains, and then we can maybe put some fill on top. This is our fill surcharge. We can try to consolidate our MD layer inside first, and then when you lose volume due to compression, then you put more fill on top to the final formation level. So this would be a partially dredged reclamation. If the question is, these days in Hong Kong, although we stress that we don't do, well, we're not supposed to dredge that much, but we do dredge routinely. For example, sometimes to maintain just safe operation in the harbors in Hong Kong, Portworks Division has to do routine dredging to level up the seabed. So there's lots of MD being leveled up, and it's perfect for carrying out research. There's various types of coastal construction that requires dredging. So even though we're moving away from dredged reclamation, we still produce waste mud. These waste mud pits are still being used in Hong Kong, although to a much lesser extent now. So even with some construction, for example, hypothetically, let's say for the Lantau Tomorrow Vision Islands, the Central Water Islands, the plan was to have a tunnel from Kennedy Town to these Central Water Islands. Now the tunnel has to be constructed, well, most likely it will be some sort of submersible tubes, right? Submersible units, just like the other cross-harbor tunnels in Hong Kong. Now, if you sink these cross-harbor tunnels, so a typical cross-harbor tunnel unit might look something like this. And then we have barges that float it out to the place we want, and then we sink these units in the ground. We can get divers to go underneath and then weld these units together. Well, these submersible units will inevitably sit on MD, so it looks like we'll have to dredge the MD anyway. So although we're trying to move away from dredged reclamation, it's not entirely possible to eliminate dredging in coastal or marine geotechnics related works at the moment. So bear in mind that we're still producing waste mud from dredging various applications in Hong Kong. In fact, this waste mud it could be useful, right? So instead of trying to just dump this waste mud into waste pits, other regions around the world, for example, in Japan, they have some quite interesting approaches where they take this waste mud here, they mix it with a binder, for example, cement. They inject compressed air in it to mix it up. And what happens when you mix waste mud with compressed air and binder is you get some sort of fill material that becomes hard and strong very quickly. So what if you could recycle the mud and then inject it back in here as fill material so it reaches strength? So could we save fill cost and looking for fill simply by recycling waste mud? So in Japan, they call this pneumatic flow mixing. Pneumatic because they pump compressed air into mud and binder and transport it into pipes, and then a long distance you have barges, and then you basically rainbow it down as fill material. So parts of different Japanese airports have been reclaimed using pneumatic flow mixing. So this is a potential opportunity. You can imagine if we have submersible tunnel units, we probably need to, so what happens is we probably need to remove some sort of berm-like structure so we can sink this submersible unit on top. So that's a large volume of mud we're wasting if we just dispose it. Can we reuse the mud? So these are potential areas of innovation for reclamation in Hong Kong. Sidetracked a bit, but so that's a partially dredged reclamation. Now, let's look at a fully non-dredged reclamation. So, just like any reclamation, we would have a leading seawall to contain our reclamation. So we have an empty layer. Underneath we have alluvium or some sort of CDG material. So now with fully non-dredged reclamation, even for the seawall, we may not have any dredging of the material. So what we can do instead is try to just build some sort of seawall on top. Now, you can probably see immediate problems here with the seawall. Is it sits on MD, which means it's highly compressible, it's very weak. So what can we do? Well, this is where, in some applications in Hong Kong, we can use stone columns. So before we put the seawall on, we can sink some stone columns in this MD layer here. So it serves as a composite foundation, and then we place our seawall on it. So in this case, we're not having to dredge the mud, except we put in a composite foundation inside the MD layer, the marine deposit layer, so that we can sit a seawall on it. Likewise, you can do other things, such as, if you like, you can put PVD drains here, then you can dump some fill material as surcharge, let it settle, and then place more fill material to your final elevation. So this would be how a fully non-dredged reclamation looks like. Now, the problem being, now, you have to use deep replacement if you use stone columns, and there's additional costs accrued. There's also technical difficulties because not everyone is familiar with how to use stone columns. There's not too much experience. The stone columns serve a few functions. Stone columns also act as drains. In fact, they're much more pervious than band drains, PVD drains, because they're much larger diameter. It's just a rock, basically a column. So it helps to accelerate consolidation, but it also takes some of the bearing load from the seawall on top. So this would be how a fully non-dredge reclamation may look like. Now, for any typical land reclamation project, you can have different types of reclamation. It doesn't have to be stone columns, doesn't have to be PVD drains. You might have areas that are dredged, some that are partially dredged, some that are non-dredged. So it doesn't have to be the same construction sequence for the entire area. Now, something interesting about stone columns, if I can draw a better picture here. So, if we have an MD layer, we have alluvium, CDG, let's say this is the sea level. We want to build some sort of seawall here, so this is, I'll choose a different color. This is the seawall. So this is the seawall. Now, interesting thing is, often we insert stone columns like this. Support the seawall, let's say. Now, stone columns are basically coarse granular material. It's frictional, right? So if it's frictional, we can expect it to follow some rule that looks like this, right? Shear resistance. Now, what's interesting, we do build seawalls like this, where it's sloping up at some angle here. What's interesting is if this is frictional material, to mobilize the maximum shear resistance, you should have some sort of overburden on top, right? But interestingly, I find it quite interesting that for some seawall constructions, we have a tapered shape here, right? So there's actually not that much overburden for the couple of stone columns here. So there's not a lot of shear resistance. Now, why is that an issue? Well, when seawalls fail, they don't fail vertically down, because what kind of load do you have? Well, if you fill this with fill, you actually have earth pressure, putting it this way, right? A typical failure mechanism might look something, it could cut through seawall, and your seawall can maybe settle and slump. This happens, reclamations fail, seawalls fail. So these kind of designs do exist, and then you have to ask yourself, does it make sense to have almost no overburden to mobilize any shear resistance here? And if we have a failure mechanism cutting through the leading edge of the seawall, is that problematic? Is that dangerous, right? Because your seawall can settle. Often for reclamations, we also use the seawall for transport roads as well. So this is sort of a contradiction, I think, in using stone columns. We should try to mobilize as much shear resistance as possible inside a stone column. So this is just sidetracking a bit, but I hope I just gave you a sense as to what the different types of reclamations are in Hong Kong. Aside from stone columns, you can also sink DCM columns. That's what they did for the third runway system at the Hong Kong International Airport. And this is essentially how a composite foundation works for the various types of reclamation methods. Now, there are, of course, other interesting things around the world. I forgot the term. There's also a scenario where, let me look at the term later during the break, but there's a scenario where you have the sea here, and we build a very tall seawall. It starts with a P, this term. They use this in the Netherlands. So what they do is, this is actually the other land that we use, okay, that we develop on. Development. So there's a stretch of land here where they use a bunch of canals, pumps, to basically just have a low-lying area. It starts with P, I'll look it up later. So they use this in Netherlands where they have a very wide stretch of land, we're talking about kilometers, where you have a very high seawall to sort of hold the water back, but you have to keep on pumping, you have pumping stations. You want to suppress sea level somehow, and this area can be kilometers, basically, before you have more development. So there's a long, low-lying stretch of land used to protect, essentially, any coastal area from the sea. This can also be a technique for reclamation. They use this for Singapore as well, Netherlands. What's the advantage of this? Well, the advantage of this is you save replacement material. If you have the right setting and if you have the right canal system, the right pumping station, you can technically suppress the groundwater table, right? But then you're probably worried about what if there's an extreme weather event, and what if the pumps fail, then this might not be such a good option, right? So there are different types of interesting reclamation methods around the world to minimize the use of film. And this was initially proposed, I think, or used in the Netherlands, and recently they used it in Singapore as well. And this area, if it's suppressed, you can use it for agriculture. You can even put some buildings inside, right? But the only issue is, it's probably quite alarming that you're below the sea level, and you constantly have to pump. It could be a bad situation if your seawall gets breached, or if your pumps fail. Because we know that water will try to flow from high total head to low total head. So the entire region, this low-lying region, starts with a P, I forgot what it is, I'll tell you later, can be submerged, right? So this is another way to save fill material. So notwithstanding, that's just a quick introduction about different types of reclamation procedures, whether it's fully dredged, partially dredged, or fully non-dredged. This is a picture of the Hong Kong boundary crossing facility, or the Zhuhai Canal Bridge and Hong Kong Bridge. Essentially, it's on a special parcel of land that was reclaimed using PVD and drains and field surcharge loading, and it's just adjacent to the airport. Whenever you go to the airport, you see this boundary crossing facility there. And various parts, I understand that various parts of the seawall, it may be wrong, but were supported by stone columns as well for this Hong Kong boundary crossing facility. And then there was also a link road that was supported by stone columns, and I think some of these stone columns may not have worked the way they were expected to. That's perhaps something you can find in the newspapers. Now, back to the topic at hand, particularly deep replacement. So why did I show these examples? Well, Hong Kong boundary crossing facility for seawalls, for example, I understand they use stone columns, and the most, I guess, pioneering case of using stone columns in Hong Kong was for DTP, they call it Disneyland Theme Park. And the interesting about Disneyland Theme Park is that they needed to reclaim that land for Disneyland in about 2.5 to 3 months. That was all the time they had. So at that time, they were probably very well experienced with using prefabricated vertical drains, because they used it for Zhengguanou as well, and various projects in Singapore. We use PVD drains. The first successful case was for the airport in Singapore, and the technology just transferred over to Hong Kong. Zhengguanou, Cheilao used PVD drains to reclaim the land. But the problem was, for Disneyland theme park, we had to construct this under a very tight schedule because it was a high-profile project at the time. And with that in mind, the entire Disneyland was not reclaimed using stone columns, only a part of it. The part that was actually the road, the main road to transport machinery, provide access, haul roads, that part was reclaimed using stone columns. And it was rationalized that PVD drains are quite narrow and small, as we saw, but stone columns can have very large diameters, which means they're very pervious. If they're very pervious, it means that you can consolidate and dissipate pore pressures much faster, especially if you throw a field surcharge layer on top. PVD layers also have smear effects, well resistance, and this is well recognized. It's well recognized in Hong Kong by that time that PVD drain designs were never quite close to what the calculated expected settlements were. They were always a little bit less. So with such a tight schedule, 2.5 to 3 months, it was determined that for parts of the reclamation, perhaps we should use stone columns. The Disneyland reclamation was actually partially dredged, if not mostly dredged. Only parts of this special road in the middle for access was stabilized using stone columns. Now, let's take a look at this particular case study here. So, I've given you the background of the Disneyland theme park, high-profile project. We needed to reclaim it in 2.5 to 3 months. There was a relatively thick layer of MD from 15 to 25 meters thick. And we had to use the land quickly to develop the Disneyland theme park. We couldn't handle a lot of residual settlement. So all that had to be done very quickly. Now, with that in mind, if we look at the map of this project, so this was the background that I've given you, and it tells you previous successful use of PVD drains in Hong Kong. So I mentioned Zhongguanou, Tianfu use PVD drains, and it was thought that we should use stone columns to accelerate the time for reclamation. Now, so here's the map of Penny Bay reclamation. So this entire area is the reclaimed land. So this was basically all ocean before, and the water just flowed through here from the sea, and there's not a lot of wave action. So it means that a lot of the settlements were quite slow, and then they could settle very slowly, meaning there's a very thick layer of MD there in between here. Now, for the stone columns, they only exist in the middle here. This was where all the major access roads were, and we needed access haul roads to expedite the reclamation of the Disneyland theme park. So this is how the overall map looks like, and the stone columns were not the entire site. In fact, as I mentioned, most of the reclamation was due to dredging. So, for this particular case, we already looked at different types of deep replacement methods. For instance, in this case, they use bottom dry heating. Particularly, they use gravel material. And before you can carry out deep replacement, you have to do trials. So you might be thinking, what does a trial mean? Well, they had to do a bit of trial and error to see how much power they needed for this vibration device, this vibroflot, to get it into the ground to the target depth. Did they need to pressurize the gravel with air pressure during dry feeding to push the gravel down? Could we compact the gravel so that we displace it properly into columns? Were the columns coherent? Could we form the target column height? Now, so they did some trials, and they decided eventually on a particular type of ambage to use for the vibro system, and also the method, how long do you vibrate before you lift up, go back down, compact, lift up, and so forth. So essentially, dry bottom feeding deep replacement method was used for the stone columns. You can see that method being carried out chronologically here. In this case, there is a casing being used. So the casing was vibrated to the target depth. Then there's a hopper at the top dropping in gravel material. And just like you've seen in the videos, they create balls of gravel all the way to the top until a column is formed. You retract the casing and you repeat until you get a composite foundation. For this particular site, they used a triangular pattern on the sides, and the spacing between the stone columns of the triangular pattern differed depending on the thickness of the MD layer on the site. So this is how they carried out deep replacement. So if you want to look at a cross-section of how this looks like, well, initially you have the marine mud here, and then you have stone columns essentially sunk in here. And on top of that, we have preloading. So with the preloading, it does a few things. It mobilizes the strength in your stone columns, and it also causes consolidation underneath. And you can probably imagine that you'll get some sort of arching behavior here, but you'll also get differential settlement between the marine deposits and the stone columns. Another thing is, during the installation of the stone columns, you're essentially vibrating the casing into place, and then vibrating everything and pushing the gravel side. So this is very similar to dynamic deep compaction that we talked about. And for this particular project, during the dynamic deep compaction or installation of the stone columns, there's actually, this created a lot more settlement than the actual consolidation of the clay layer. So the most of the settlement was caused by the installation of these particular stone columns into the mud. And of course, on top, we always combine, as I mentioned, some sand fill layer to provide preloading on top. And this sand fill layer was also compacted using deep dynamic compaction. So this was essentially the cross-section of a typical profile at the Penny Bay site using stone columns. So to give you an indication, I mentioned that the spacing of the columns would differ depending on how thick the mud is. And they use different types of spacing, and although it's a triangular pattern, I mentioned it's a dry bottom feed method, but to help the vibrating device and casing go into place, they did some pre-flushing using air and fluid to get that casing into place. They place a surcharge on top, as I've shown you, to provide a bit of loading to mobilize strength and to create settlement. And this fill layer was also vibro compacted, which caused additional settlement. Now, by using stone columns, preloading, and dynamic compaction, this particular project was able to reach a stable consolidation, or stable settlement pattern in just 2 months' time. The bulk of the settlement was caused during dynamic installation of the stone columns. And if you're wondering what type of theory they used, well, they used the exact same theory as we learned in our class. We used Barron's theory, Carrillo's theory, Terzagh's 1D consolidation. So when we did the drain example together, they estimated the consolidation due to the stone columns using the same theory, albeit we look at it in terms of drains, and they just treat the giant stone column as a cylindrical drain rather than a prefabricated wick drain. Right? So I'm just trying to link what we've learned together with what we see here. And of course, eventually, when your marine mud is probably here initially, and it settles, and then you get protrusion of your stone columns on top. And the stone columns have to be founded on some sort of competent alluvium or CDG layer. That's how it looks like, and you can probably see that the denser we install these stone columns, the faster the consolidation. So for a thicker marine area, because the marine deposit would not be uniform, right? Some areas might be thicker, some areas might be more shallow. So for the areas that are thicker, what we would do is probably install these stone columns at a denser triangular pattern so that the path between columns is much smaller. That means you have a quicker dissipation of excess pore pressures from surcharge preloading. So that's why they vary the triangular spacing of the stone columns. Now, that's all I want to share with you in terms of deep replacement, and just to showcase how we use stone columns for Penny Bay. Now, I'm going to transition to intermediate topic, and then next class we'll go to chemical means. By chemical, I mean grouting, and also deep cement mixing. So, the transitional topic I want to go to today in between deep cement mixing and grouting is drainage, dewatering, and geosynthetics. I just want to tell you what these are because they're so commonly encountered in Hong Kong in the geotechnical industry. In fact, some of the first things you encounter as a young geotechnical engineer when you go on site is a pumping test or dewatering, because a lot of our infrastructure is actually constructed really close to the ocean, and we're finding ourselves constantly fighting against the ocean to try to suppress the groundwater level so we can carry on construction. Now, you might be thinking, why is this related to ground improvement? Well, we understand geotechnically that if we can reduce excess pore pressures, we can increase effective stress. And by increasing effective stress, we can increase the stiffness and strength of the soil. So dewatering and drainage is a very significant component for geotechnical engineering. Particularly for most projects that are in coastal areas, we need to dewater. And the various types of ground improvement I talked about, for example, over excavation replacement, if the groundwater table is too high, I mentioned we have to dewater first. So conceptually, we can talk about it. In terms of theoretical calculations, it might be a little too heavy for you, but I just want you to understand what a sump pump is, for example, a D well, O well. It might be advantageous to know what these are before you embark on your career as a geotechnical engineer. And another minor topic that I threw into this transitional topic is geosynthetics. Why am I talking about geosynthetics? Because geosynthetics are so commonly used for ground improvement. In fact, when you go into the workforce, you'll notice that you're constantly bombarded at conferences by different manufacturers of geosynthetics. And then there's different terms: geogrid, geocell, geofabric. What are these things? What are they used for? So I hope this gives you a bit of an introductory, lesson to what these topics are. So for this transitional topic, there are a few outcomes. A good geotechnical engineer should be able to identify what are potential failure mechanisms. This is the most crucial thing that we must know. For example, if you want to take the MHKIE license later on in your career, you can't just be a specialist in one type of geotechnical structures. For example, if you've been doing slopes your entire life, you'll find it quite difficult to jump into an MHKIEG exam and just talk about slopes. You're expected to be well-rounded. You have to understand excavations, tunnels, slopes, reclamation. That's the premise of getting the geotechnical license, to be well-versed. So to be well-versed, you have to understand, when you look at particular geotechnical infrastructure, how can this fail? And you should be able to tell the examiner that, look, for this cofferdam, we can have piping, hydraulic failure, we can have kick out, for example, and you can identify all the failure codes. So I want to talk about potential geotechnical failures caused by water, and by suppressing the unnecessary movement of water or reducing pore pressures, how can we improve the ground to get the response that we want? So that's the first expected outcome. The second outcome is that, what do we expect to happen when we reduce pore pressures in the ground? There are, of course, adverse effects. Anytime you dewater, you can expect to potentially cause problems outside of your cofferdam. You can cause consolidation settlement, as you've learned from your consolidation module in this lecture. And if you dewater, what happens if there's recharge, right? So we'll talk about these things. Other aspects of geotechnical ground improvement includes filtration, separation. So we'll talk about what these terms mean. And we'll explain the fundamental differences and relationships between drainage and dewater. So we'll cover some of these concepts. Nothing too, I guess, requires too many numbers in this module. So, a quick review. There are a few groundwater conditions that we commonly deal with in geotechnical engineering. We have hydrostatic states. We love to deal with hydrostatic states because it's simple. It's the depth times unit weight of water gives us some sort of pore pressure. We refer to it as hydrostatic when nothing's moving. You can also get steady state seepage. Steady state seepage is if you have, as the term steady implies, no change in time. You may not have hydrostatic, you might have flow, but if the flow is steady and the flow rate's not changing with time, then you have steady state. The third condition you have is, well, you don't have steady conditions. Your soil is consolidating, pore pressures are constantly changing. You may or may not be able to capture the change in pore pressure because of the rate of dissipation or the rate of generation. I remember we had a quick chat with a student outside this lecture. In geotechnical engineering, usually, if you know that the pore pressure is either hydrostatic or steady state, you could probably calculate the pore pressure. Under these conditions, I would say you know the pore pressure. And if you know the pore pressure, you should carry out effective stress analysis under these circumstances. It's only if you don't know the pore pressure that you're forced to carry out total stress analysis. So if you're asked, why do you have to carry out effective or total stress analysis, your answer should be, well, you should always carry out effective stress analysis if you know the pore pressure. And what do I mean if you know the pore pressure? Well, if it's hydrostatic or if it's steady state, then you can calculate it, right? But if it's transient, for example, you have a very fast rate of loading and the pore pressure can't even be generated or dissipated or detected by the pore pressure measuring device, you don't know the pore pressure. And you know that soil behavior is governed by effective stress, right? It hasn't been disproven by anyone since Terzaghi came up with this concept that saturated soil mechanics, I'm talking about saturated, meaning your pores are completely filled with water or they're dry. It's governed by effective stress. If you know this to be factual, then you know, if you know the pore pressure, you must carry out effective stress analysis. There's no questions asked. But in geotechnical engineering, sometimes it's not so clear cut. We don't know the pore pressures because excess pore pressures have not dissipated due to rapid loading, rapid construction. So under those circumstances, we're forced to check effective stress conditions and total stress conditions. Effective stress parameters for strength, phi dash, C dash, total stress parameters are CU or SU. So bear that in mind if you're not quite sure when to use effective stress or total stress. Total stress is a gross approximation of the problem at hand. Since we don't know how to differentiate how much load is the soil skeleton carrying, how much load is the pore pressure carrying, then we're forced to say, look, I don't even know how much pore pressure there is, so I don't know how much the skeleton's carrying, so I'm just going to use total stress and treat the solid and the water as one continuum. I don't care, so I use total stress analysis. Right? So bear in mind, groundwater conditions, these are three general states that we care about. Hydrostatic, steady state, consolidating, and this of course is something that you can review, but should be quite ingrained in your mind as a geotechnical engineer at this stage of your degree. How are we doing for time? Shall we take a 10-minute break and then we'll get back to things?
2日點 rehearsal？咩啊？未整。唉，我整咗，望咗聽唔聽？呢度PowerPoint 5分鐘啊！佢咁14、17啊！
我淨係做咗後邊嗰個收嗰 part，但係前面嗰啲
14、17，跟住哇屌34，24啊！
有冇出回收嘅話係出成
我淨係寫咗個 result 咯。
因為兩樣嘢係咯，
係咯，我都冇備收。
都係喎。
我之前呢啲出嚟都差唔多要邊晒。
份文件係12月先做。
啊！大鳩我
啲 result 咧。
我冇 progress 喎，點算啊
？result 咪係嗰幾個 part 咯。我知你聽你文件係10個 part，
9月
所以收少交。
3個月點出 result 啊？
13個 test 上 result 啊。
唉，第一個未啊，冇分啊！
結不唔到啊！
你講咩啊？
呢個俾咗分你。
我未啊未啊。
太多字。
衰啊！俾翻我。
太多字啊！
算啦，未啊！
唔係好少
第一份最少。
所以話日兩個得廿3萬 test range test 同埋 Q test 兩個 test， 即係 CU 即係 SU 即係
range 好似係 check residual，
係意思做，但係
唔係 residual 係點讀啊隻字 residual 啊 residual 啊 residual 啊唔係啊呢個啊你點讀啊 residual 係你嘅字嚟嘅喎，咪咯，
係咩？唔係同一樣嘢嘅咩？
所以 residual 係第二樣嘢。
哦，
我諗佢係咪同 UU 係
咁即係空嘅啫。點解全部一齊望我邊做乜嘢啊？冇關事嘅喎，冇關事嘅喎。哎呀，做乜嘢？哎呀，可以繼續，可以繼續。咩啊？因為練得多咯，太勁。唔係，我冇特登練喺我房背啊嘛。
時光機練係
個係
即係你呢度就係
咁樣放落去。
嚇！真係㗎？
即係放落去啲梳攞
太大隻啦，冇計。
借咗力，
即係需要有個教咗係教一個 range 咁樣。係啊，需要教。有兩個，一個 range 一個 VAN 嘅。即係 VAN 係啊，我想呢個同埋嗰個。
冇啊，冇嘢望啊呢個。
下個 motivation。
我如果要
冇嘢望，
你先48啊！黐線。
唔係有成好多嘢都係 convert matter，應該大概成12個。
其實我諗緊係咪到25？
交俾咩兩份嘅？
唔係嘅，
交俾
PR2直接交俾你個係話
但係唔係交俾 CES 嘅咩？
兩份都要喎。
即係同一份嘢要嘅。
一份要交俾 MIT。
咁可唔可以交兩樣唔同嘅嘢？
我諗住交兩份唔同嘅嘢。
你都係咁交啊？
梗係啦，交俾 Sergio 就唔會咁多口水嘢㗎啦。
係啦，交俾 Sergio 可以唔使訂咁多拍 Mabel 要嘅
諗住
嘛
Mabel 嗰啲我
rehearsal 啊嘛。
14號。
係啊，14號啊。幾年看看。
佢 expire 交同一份嘅，但係我哋係交佢兩份。
但係我哋係0%嘅。
係0%啊，但係都要準備。總之而家要做啦。
我以為佢交佢 model 嗰份佢已經都冇交佢師傅。
而家直接嘅。
不過因為嗰份太過英文，所以分兩份交。
係咯，我呢啲字太難。
嗰份 Sergio 嗰份就 cut 到25萬。
呢個係要分到25萬，寫你應該係計。
死佢算啦！
如果計咁唔使寫。
計嘅話，其實我幾寫嘅，都10版內10版內。
呢個算啦。
因為但係我見嗰啲人寫百幾版嘅，呢個咪刪咗。
你做完
係啊，我見到啲人翻到 report 寫咗百幾版。係啊，
好似40版。
係啊，係啊，但係我見到有啲 source 係寫，即係有啲
應該唔夠 content
阿 Lego 都收到啲咩80幾版。
你要打開佢先得。佢嗰個 extension，但係你開想撳個 play button。
咩啊？咩 music 啊？
今晚俾你啊嘛。
係有咁嘅嘢嘅咩？我哋去到咩？食完嘢都
11點正啦，11點見見。
去睇 Maple 喎。
11點嘅。
11點見我睇機仔啦。
咩事啊？
立志有個音樂叫做係超面上超面上
幾點至幾點啊
？7點到8點到
8點到11點，即係話3個鐘都有人 present，咪有人表演。
我覺得我哋食埋飯可以過去撐場。
可以撐1個鐘嘅啫喎，都
係啊，我 roommate 搞。
都係佢負責㗎，即係佢係主辦。
係咩？真係搭 band
都完全唔知嘅，係咪 email send 過？
我都唔知。
佢同我講
好消息。
係。
我陳奕迅嘅專輯啊。
OK。
我唔知遲啲上10日。
應該完全唔知嘅，等我 check 下先。
Music Live 啊？
係。
等我 check 下啦。
有 music club 喎。music club 冇呢個冇。
摩天輪。
music 咯。
摩天輪。
哦有喎，見到喎。
好嘢。
我哋 walk in
哦嚇要 rap 嘅咩？仲要30條喎。
係啊。
咁你 rap 咗啦？咪咯。
喺邊度？
佢係啊，3樓 studio。
咁3樓其實有機會開始。佢其實呢個，
即係佢寫咩啊？康康。
阿年啊？
唔知啊，費事去旅遊。
我哋嗰邊勁喎。可以聽
好啊，你唱歌實去。
我哋嗰邊係個 star 係好唔同。
Connect HKJ。
最經典嘅 U 咩一定係戇鳩仔。
好勁啊！有 nickname 嘅整喺度瞓。加8唔止。哇！好多要我唱歌嘅人，唔唱歌，拜拜。真係，我有
因為你入去
SSS
入去係要唱歌定係聽人唱歌？
即係你哋唱
聽人唱歌喎，
定係完全都係唱歌？
會㗎。
佢哋叫我。我哋兩個人先唱歌。
勁啊你！哎呀，夠啦我今日，好攰。你嗰邊係咯，我哋嗰邊而家係，即係整個法，即係整個4分法。
我之前即係可能有2種船，最大最細。係啊。同埋個 contractor 幾唔同咁樣，即係佢嘅 case 都唔同。最多2種。
似都有個佢會
唔知做乜。
雙方面，
你講得玩嘅。係廿尾爹嗰邊嘅。
let's carry on again. I think our break is over. So, carrying on with review, why are we concerned about water in geotechnical engineering? Some of these are quite obvious. Well, at the top here, we talk about various sources of water in Hong Kong, predominantly from precipitation and obviously being adjacent to the sea. You have very high recharge. You have a cofferdam inside the sea as well. For slopes, we're worried about infiltration from heavy rainfall. Other regions around the world, you can have melting of snow and ice. You can also have seepage from higher total head and lower total head. Another question during interviews is if they ask you what controls the seepage of water, make sure you say total head, right? It's not right to say pressure head or velocity head, it's total head. You have elevation, velocity, and pressure, right? Sometimes we just think that higher elevation controls flow, but that's not a complete answer. It's almost a trick most of the time. You want to hear total head, which comprises 3 elements, right? Because you can also have artesian aquifers. So anyways, just off the top of my head, they always like to ask, total head controls flow and Darcy's law. Anyhow, so you can also get seepage from higher ground here. Yeah, I guess. Dams, lakes, and rivers. You can also have rising groundwater, and you can have atmospheric soil interactions, capillary effects, vapor from high humidity. So these are sources of water. And how do they adversely affect geotechnical infrastructure? Well, anytime you have water that's in excess of hydrostatic conditions or excess pore pressures, you have a reduction in effective stress and a potential loss of strength or shear resistance in the soil. You can also have increased hydrostatic stress behind retaining walls, because if your retaining wall is completely retaining the entire body of water, you have to consider the additional hydrostatic stress as well, as you've learned from your retaining wall class. So that's another detrimental effect of water. You can have seepage. Seepage is quite problematic if it can cause the washing out of fines. If you have very high seepage, you can wash out all the fines in your soil. You can have piping, uplift, hydraulic failure inside excavations, where the seepage reduces the effective stress inside your excavation, and it can cause you to basically lose passive resistance inside an excavation. Uplift, same thing. You can have, for example, with a footing, if the pore pressure is too high, you can lift up your entire footing. If you have a footing that's hollow, it's like a culvert, it's much lighter than the applied uplift pressure. It can also lift up a culvert. Water can also cause swelling, shrinkage, collapse. These are for special soils. In other places around the world, you're probably worried about freeze-thaw action in the north. As I mentioned, anytime you have high velocity of seepage, you're worried about internal erosion, loss of fines. It can be superficial on the surface, or it can be internal. So the internal erosion of fines to change your soil. We can actually mitigate some of these things using geosynthetics. You can mitigate it using filters. By filter, it doesn't have to be a piece of geosynthetic, it can be a separate soil layer in between with a different gradation, as you'll see later. So what you see on the right of the slide here is just an example of something simple, such as a highway, and how water can have an adverse effect to it. For example, if you have something pervious, you can have infiltration into the pavement. With the new concept of sponge city, you can see special types of concrete or pavement where it allows water to not pond but go back into some hydrological system and recycle itself. You can also have runoff on the side when it rains. Let's say it's not pervious. You can have seepage from higher ground, as we mentioned. You can also have capillary action. What does that mean? Well, we know that if you reduce the water content in the soil, it can become desaturated, and then you have matrix suction. And the more water content you remove, the higher matrix suction you get, which is sort of good for your soil. But matrix suction is transient, right? When it rains, you lose it again. So we often don't consider it in routine design. So that's what we mean by vapor movements and capillary action. Vapor movements can be caused by different relative humidity. If you have different humidity, that can affect the matrix suction as well. And you can also have obvious increase or decrease in water table. So this slide is essentially showing a summary of the different sources of water, and we've explained adverse effects. In geotechnical engineering, we have different methods of groundwater control to be routine. Most of these things, if you want to design them, are probably designed using GeoStudio SeepW. So when you go into geotechnical practice, if you want to see whether a particular groundwater control measure works, you'll probably just run a seepage or SeepW analysis. It seems quite odd to draw flow nets these days. Probably doesn't happen that often. If you can, that's good. So the first type of groundwater control is providing drainage. What does drainage mean? Well, it's just creating a very pervious layer of material to create a preferential flow path behind your infrastructure, inside your infrastructure. So here, this is a relatively pervious soil layer, and in front of the soil layer, there's something we call a geotextile that's wrapped here. We'll talk about what this geotextile is in subsequent slides. You can also have some sort of pipe here to enable water to come out of these holes that you often see in retaining walls. Some of them are called weeping holes. You see them as you walk past a retaining wall, for example. So one way is drainage, creating a very pervious blanket behind a structure to alleviate hydrostatic stresses that build up behind it, to minimize lateral load on your retaining wall. So that's one use of groundwater control. We'll talk about these in a little bit more detail. Another one, if you look at the top right here, is dewatering. And this is a very routine thing in Hong Kong, dewatering. You can sink pumps to different elevations in Hong Kong. You can have deep wells, you can have shallow wells, you can have sump pumps. For those of you that worked on construction sites in your summer months, you probably have heard these terms. They probably throw a sump pump there, D-well, O-well. O-well is for observation, we call it observation well. D-well is a dewatering well. You also have recharge wells, where you try to put water back in the ground if you reduce the water too much. So these are the three types of wells you see. In this case here, you can see this. You might have a groundwater table like this initially, and if you turn on a pump, you can actually suppress the groundwater table to something like this. And if you, well, the groundwater table is here, but if you reduce it, then you can go inside your excavation and start construction. You generally try to at least suppress the groundwater table to be about 1 meter below the working elevation. Otherwise, you can get very swampy inside a construction site. So that's what we normally do. There's also something called a pumping test. We'll talk about it later, but dewatering is another means of reducing the water. And often we can reduce the water table so we can do other types of ground improvement, such as chemical replacement, over excavation. If we don't dewater, sometimes we can't do it because we're constantly fighting with the recharge of water. The last type of groundwater control that you see at the bottom here is often just creating some sort of membrane, some barrier. A common application of a barrier may be landfills, for example. You have some sort of geomembrane, geotextile, just to prevent seepage of water through a particular layer, because there are leaches that are harmful to the environment. So even geotechnical engineers play a very significant role in geo-environmental problems such as landfill design. In fact, there are some very famous geotechnical engineers that focus mainly on barrier design. And barriers can be clay layers as well. It can be like a very thick clay layer, which is relatively impervious, right? It can be used as such. So, and what you see here are three means of groundwater control: drainage, particularly dewatering, and barrier. So underneath here it says drainage removes the water either by gravitational effects or pervious layers. Dewatering uses pumps by creating total head differences. Barrier is just some sort of cutoff. You can also create a barrier by using grouting, as you'll see later on. You can create something we call a grout curtain, for instance, underneath the toe of a sheet pile wall to improve hydraulic cutoff, as I'll talk about in a bit. Drainage promotes water while barrier prevents it. So that's the fundamental differences among the two. So I want to talk about something quickly. You'll see these terms pop up quite a bit called geosynthetics. And you'll see different types of terms. You probably see these words all the time, even periodically throughout our earlier modules. We talked about geotextile, geogrid, geonet, geomembrane, geocell, geocomposite. So what are these? They're not the same thing. We should not interchangeably say a geotextile is the same as a geogrid or geomembrane is the same as a geotextile. We have an over-encompassing word that we can put all this under the same umbrella. We call these geosynthetics. Geosynthetics are any type of sheet type material that we create as engineers. They're synthetic to serve one of the three purposes that we talked about. One of the purposes is drainage, the other was barrier and dewatering. So how can we use geosynthetics to create these types of groundwater control? So if you look at the bottom table here, before we look at the bottom table, these are common words that you'll see throughout your geotechnical career, and it's important not to, well, geotextile shows them twice. It's important not to mix up what these terms are. So the table is probably overwhelming in terms of check marks, but we can go through each of these to try to understand a bit better what their primary function serves as. Of course, some of these geosynthetics can be used for various types of applications. Separation may be trying to separate, let's say, a fine silt layer from a coarse gravel layer. You don't want your coarse gravel to mix with your silt material because you're trying to design some sort of foundation for your highway embankment, for example. That's what separation is. Filtration. For our PVD drains, we don't want fines to get into our PVD because we get well resistance. So that's the use of a geosynthetic for filtration. And we've talked about PVDs already. Obviously the PVDs are wrapped in some sort of geosynthetic, although we haven't talked about geosynthetic yet. The purpose of the geosynthetic there is to minimize the effects of filtration. There can also be used for geosynthetics to enhance drainage by providing a preferential flow path for water in the ground. We can also use geosynthetics, as you've seen in your retaining wall class, to increase the strength of, let's say, a mechanically reinforced wall. We can actually increase shear resistance by placing a layer of geosynthetic, so on top another layer, and creating this sandwich effect. And it can provide tensile resistance in the soil. We know that soil is not good at handling tension, but geosynthetics are. So if we create a mechanically reinforced earth structure, we can take a lot more shear resistance because we provide additional resistance. In river type applications, we can also use geosynthetics for erosion protection, as you'll see in a bit. Last but not least, for landfill applications, or you just don't want any leach in, we can use them for barrier applications. As you can see at the top, it appears that geotextiles are the most versatile Geogrids are purely only for reinforcement, as you'll see later. Geonets for drainage. Geomembranes can do quite a bit in terms of erosion protection, barrier separation. GCL is a geosynthetic clay liner. It's a geosynthetic, but there's clay inside, so it's really good for membrane effects or separation. GeoCell is predominantly for erosion protection, and then geocomposites, as the word composite means, you can use it for a wide range of effects. Geosynthetics, as you'll see later, can come in various types of fabrics. They can be woven, so it looks like our clothes, or it can be non-woven, can be just pieces of plastic connected together. As you'll see, it can have a wide range of shapes, sizes, and materials. So, the first type is a geogrid. Geogrid is mainly used for reinforcement purposes. So you can probably look at a picture here of a geogrid. They come in various patterns, can be square, can be a triangle, can be uniaxial, but it's just a very strong piece of, it looks like a plastic sheet actually. You can see that these plastic sheets are very pervious. In fact, they use this for some sort of highway application here. They're so pervious that you're probably not going to use this for separation or membrane, right? And the plastic's actually quite strong in terms of tensile resistance, right? So we can use this to our advantage. So I hope this video works. So an example of how geogrids are used in day-to-day geotechnical design for ground improvement, very similar to other types of ground reinforcement. So the example here is there are two boxes. One is just soil. And he's going to stand on this one. Well, it's not going to stand on it yet. And then the second one is he's going to do this like a mechanical reinforced wall. Lift of soil, place geogrid, another lift of soil, another layer of geogrid, until he gets to the top. So then he's going to show the substantial improvement in shear resistance due to added tensile resistance from the geogrid. So for this first box, there's no geogrid, there's no reinforcement, and these two assistants will pull it, and there's no tensile resistance, less shear resistance, right? And it just flaps. The second one, on the other hand, has 3 sheets of geogrid, and I just want to showcase that geogrid is usually used to enhance shear resistance of soil by enhancing the tensile resisting component. So we can use geogrids as a form of ground improvement for retaining walls, for slopes, for embankments. We can increase the bearing resistance of geogrid as well. So if you want to improve bearing resistance, you can put sheets of geogrid underneath a shallow foundation, for example. That can help you increase bearing resistance. So you can see here it's quite substantial. By using the tensile resistance from the geogrid, you can improve shear resistance of the soil. So that's the first type of geosynthetic, geogrid. Very common tool that geotechnical engineers use. Can you do calculations for it? These are generally commercial products where the manufacturer will tell you what the added properties are, what the strength parameters are, and you would use them according to what your application is. The next type of geosynthetic is called a geotextile, and what I mean by non-woven and woven is, if it's woven, it's like a yarn shirt. You can see the patterns almost if you're weaving yourself. If it's non-woven, it's probably just heat pressed, a bunch of fibers together. So you have two types, and the point of the geotextile is also for reinforcement. If you pull your shirt, your fabric, you have quite a bit of tensile resistance compared to soil on its own. So you can also line geotextiles to minimize or increase shear resistance in the soil. We can also use geotextiles for filtration if we know the size of the openings for a woven geotextile, for example. It's quite versatile, geotextiles. So I don't know if this works, hopefully it works. You can also use
Geotextiles can also be used for erosion control. Where turbulent waters may erode stream banks, geotextiles may be installed to dissipate the energy and to prevent excessive sediment buildup in waters, which is detrimental to downstream ecology.
Okay, so even on construction sites, if we're worried about a lot of flow of water on the surface eroding, let's say a foundation, we might put some geotextiles there. So you'll see black fabric, and it's just to minimize the effects of erosion due to very high rates of seepage. So that's what geotextiles can be used for, and you can also see that geotextiles can be used for separation as well. Separating fine gravel from maybe clay, for example. That's another use of geotextiles. We also have geonets. Geonets are quite versatile, but they have a much higher degree of permeability, meaning that you can have a lot more flux through it. This can help as drainage material because you promote the flow of water through this material. So if you want to have water pass through, then you should use a geonet. Net implies that it has openings that are quite substantial and enable drainage. It also has quite a bit of tensile resistance, but the main use of the geonet is, of course, to promote drainage. And on this slide, you see various applications of these sheets of geonet. Here's a zoomed up view. You can see that the openings are actually quite large, and it would be a nice promoter of flow. And the fibers here are also quite thick. You have high resistance for failure as well, some tensile resistance. So that's geonet. Geomembrane, as the word membrane denotes, is something impervious. It's almost meant to be a barrier. You can have, in this case, you have different textures. There's a rough and smooth membrane. Here looks like some sort of pit to store contaminated material. We put this lining on and we try to minimize infiltration of whatever we place. Could be waste, leach it into the ground. So geomembrane, the word membrane implies very low permeability, low hydraulic conductivity, and it's generally used for landfill and so forth. We're talking about hydraulic conductivity because it's only the conductivity from water. Permeability can be the perviousness for other types of material, like oil can be one, so that's why we call hydraulic conductivity often in geotechnical engineering. So anyhow, so that's a geomembrane. We also have a GCL, what you saw on the table earlier. We call this a geosynthetic clay liner. Clay we know is very impervious. So what's interesting about this is if you open up one of these, you see clay inside. So it's here's an example. One, you have fabric that's closed off. Inside and between there's a thin layer of clay. And we know that clay is very impervious. If you wet the clay, you can get a very nice barrier system as well. So GCLs are often used to prevent infiltration, leachate, also used for barriers for landfills and dams. The advantage of using GCL is that in this case, these are in the order of millimeters of thickness. If you had to use clay instead of GCL, there are a few problems. You need a much thicker layer of clay. Clay is susceptible to desiccation, drying, shrinkage, crackage. It's very difficult for the contractor to compact the clay to not have problems. So this is where GCL comes in to be advantageous. You can put a layer of GCL on. It's very thin. You don't need maybe a few centimeters thickness of clay layer. You're not going to get constructability issues because of cracks, non-uniform compaction. So GCL is also a barrier. So this is a type of geosynthetic. The next type of geosynthetic is geocell. This is purely reinforcement, as you can see. Essentially, these are just grids. We call them geocell because cell stands for cellular. Cells can be in any shape or form. You can see that it's like a rhomboid or diamond shape for this one, and it's like a circular oval shape for this one. And you can imagine this plays a very similar effect as the geogrid, except the geocell here provides additional natural resistance through the tensile resistance of this plastic material. So geocell, just like geogrid, is predominantly for reinforcement of geomaterials. You can imagine that in the same video I showed you, if you use geocells versus not using geocell, you're going to get a lot more bearing capacity because you have additional natural resistance through the tensile resistance of the plastic. So that's how it works. You can also use this to distribute loading, so it's not so concentrated in a particular area and increase phase of resistance. Now, so we're thinking about, can we use geocells to improve bearing capacity? Well, yes, you can. So maybe you don't need to carry out over excavation. You can carry out, use just a thin layer geocell, and that might help you distribute load, right? Although we can't calculate this stuff, these type of technologies exist for ground improvement. So it's nice to know about the options you have at your disposal, but then of course you have to trust your manufacturer when they tell you the specs, how much improvement you get in terms of shear resistance, lateral resistance. These are obviously proprietary products, and you have to ask your manufacturer, based on their experiments and testing, what's the added value of using this. So more often than not, this type of geocell is used for highways as well, to increase bearing capacity, and very similar to geogrid, as I mentioned. I think this is the last one. So among the geosynthetics family, there's also something called geofoam. Not something we deal with a lot in Hong Kong. Geofoam, as the word implies, is just a block of foam that you take if you buy a computer monitor. It's inside the box, except this is a very large piece of foam block. It's lightweight and it can be used as a fill material. In the US, geofoam has been used to stabilize embankments for highways. Perhaps the only problem is degradation of this material. Is it toxic foam? Is it flammable? These are perhaps some of the concerns, but it's quite modular, almost like Lego blocks, and it's used for some highway projects around the world. Here, this is a video. It's not a video. Anyways, so this is geofoam, the last of the geosynthetics. We also characterize it as geosynthetic, and lightweight is the advantage. And you can see that by having a lightweight fill material that can distribute the stresses, we also minimize the bearing loading on the soil underneath. So it's a twofold advantage: distribute loading, and it's very light, doesn't add additional surcharge. So that's the geofoam for you. Okay, so that's the geosynthetic family that I want to talk about. Now, there's also one type of groundwater control measure, such as filtration. Filtration allows for flow, except it tries to not let particular particle sizes pass through. As I mentioned, you can create filters using soil on its own just by playing with the particle size, or you can use a geosynthetic. Now, if you look at this picture quickly at the bottom, you can quickly see the advantage of a geotextile. You have a very uniform and very thin layer, but if you try to create a filter using soil, it's much thicker, and you could be susceptible to constructability issues, non-uniform thickness. The principle of a filter is to not let a particular particle or target particle size through. And you can see from this picture, we don't want these finer particles to essentially fall through, percolate through these much larger voids. So to do that, we add an intermediate filtration layer in between. And this is a very common type process used in the field. And there are various types of empirical criteria. For example, D95 needs to be a certain size larger than a certain size D50. So you see these types of criteria used quite often. And the simplest form of filtration you can probably imagine is our PVD example. We just don't want fines going into our PVD drains. We can just use a geotextile filter in this case. There are two basic criteria you remember for PVD drains particularly. Even though you want to serve you want the geotextile to serve as a filtration layer, you still have to consider, is it pervious enough? For example, the point of a PVD drain is to enhance the dissipation of pore pressures. If you have permeabilities that are too low, you're going to prevent rapid dissipation of pore pressure. So a very effective filtration or filter will cater for two parameters, particularly permeability and also the ability to retain finer particles from entering whatever layer you'd like to use. And for filtration, there are three major types of filtration. The first one is of course total filtration, which acts as a membrane or barrier. You're not going to let any particles pass through the membrane that you set. This type of application is good for preventing piping failure or anything with excessive seepage in the ground, such as excavations. You have optimum retention. You know that some particles will pass through, but at the same time, you can tolerate that. Most filter applications are optimum retention. If you have total retention, you also suffer from forming a layer of impermeable material that gets blocked up because you try to achieve total retention. So optimum retention would be, okay, I know that some fines will pass through, but at least we're not bleeding fines out continuously. Then you have partial retention. Partial retention is a controlled loss of fines. Optimum means we want some target, but partial retention means the design is to allow fines to pass through, albeit at a controlled rate. So these are the three types of filtration. Now, in terms of applications, we often use filtration for what we learned so far, PVD drains. Anytime we have some sort of, even on a slope, we might put a drain at the top here and we have a pipe. Normally what we do is we often wrap the pipe around with some sort of geosynthetic to serve as filtration, so this pipe doesn't get filled up with fines and we lose capacity to use this type of drain. When we put in raking drains inside slopes, we also wrap these drains up in some sort of geosynthetic to filter out fines. So these are different applications of filtration devices. And as I mentioned already, there are advantages with using geosynthetics over granular drains. Of course, you can also, instead of using a single sheet here, you can put different sized particles around the drain so that a particular size of particle doesn't get through, but the most effective is probably just geosynthetic, but geosynthetics do wear down with time, they get clogged up as well. So that needs to be bear in mind. If you look at filtration from a mesoscopic point of view, you can see these two pictures at the top. One is if we really zoom in to a filter has some degree of perviousness because there are channels inside this filter to allow particles to pass through. Now, if, let's say this was a PVD drain and you let some particles arch in front of a channel, for example here, you can block it off. Another way is if you let particles accumulate inside the filter, this can also block it off. So these are the two main mechanisms for blocking off the filter, and that's also why we get well resistance in PVD drains. So this is just a zoomed in view of how filtration works, and how a geotextile works. If you zoom in, it's just a series of channels inside, and there's two main forms that we talked about. You can have arching at the surface, or you can have cloggage inside your filter system. The two terms, filtration and separation, need to be distinguished as well. For separation and filtration, both try to separate, not separate, both deal with dissimilar materials. For example, with gravel layer on top of the silt layer, or clay layer on top of the gravel layer. Both of these deal with dissimilar materials and try to prevent geomaterials from crossing some sort of interface. You need a filter when there's substantial water flow to carry finer material into coarser material with much larger voids. That's when you need a filter. For a separator, you need it when the interface is subjected to some sort of cyclic loading. So it could be a highway. When car tires pass through a thick embankment, you get cyclic loading. And the cyclic loading can cause a migration of particles among different types of layers underneath your foundation. So the difference between filtration and separation is one, filter, you're dealing with water flow. With the latter, you're dealing with cyclic loading. So at the bottom here, what happens if you have cyclic loading? Well, you'll get these large particles moving across, up and down. If you have a nice geosynthetic, then you can maintain a coarse grained soil on the top and a fine grained soil on the bottom. Some other salient points to mention when we want to distinguish between filtration and separation. If you want to create a filtration effect or to use a geosynthetic as a filter, you're most focused on void sizes or opening sizes. In contrast, if you want to use a geosynthetic as a separator or a separation layer, you probably just want to make sure you can withstand cyclic loads. So it has to have pretty high tensile resistance as a separator device. So these are the two main design concepts that we have to care about. Other aspects subjected to cyclic loading, you also generate excess pore pressures. If you generate excess pore pressures, you get a head difference. If you have head difference, then you get seepage, right? So all of these things need to be considered. But in essence, if you look at this yellow box at the bottom, the difference between filtration and separation is that if there's water flow between two layers, then you're looking at designing a filter. And if there are dissimilar materials subjected to different loads, you want something to separate. And then you can take a look at all these fine details on your own accord. So what should we use in terms of geotextiles to achieve filtration or separation? Well, for a separator, we can use geotextiles. High tensile resistance, you remember? So it's like cloth, can be woven or non-woven, doesn't really matter. You can also use membranes for separator, but membranes are relatively impervious. So they're not good for filtration, right? Geogrids can be used as a separator as well. You just have to get a very small grid size or grid opening to make sure a certain type of material doesn't pass through, for example. Filtration, you really need to ensure that water can go through. That's the main criteria for it. So these are the main geosynthetic choices if you want to design a filter versus a separator. So that's all I want to talk about for groundwater control using filtration and separation. Now for drainage. Drainage is just creating a very pervious layer that you can promote the flow of water, whether it's gravitational or a change in the hydraulic gradient behind some sort of structure. Drainage layers need to be highly pervious. An example of a composite drain, if you look here, you have some sort of geofabric, and then you have added tensile resistance, but it's quite pervious. So you have sort of a grid material separated by two geofabrics. So this is an example of a geotextile. As we mentioned, if you look at this example here, you can actually make a drain without a pipe. you can just take coarse gravel material, wrap it in some geotextile, and it can function as a pipe or a drain layer. This can be placed on the top of a slope to minimize infiltration into the slope, for instance. So for drainage, anything that promotes the movement of water through it. So we don't want anything impervious. And as I mentioned, geocomposite, geosynthetics are perhaps the best. The problem with drainage is always cloggage, right? For PVD drains, we're worried about well resistance. For these types of press drains at the top of slopes, we're worried about when they clog up and then they don't function. If these don't function, then water will tend to not go through here, and for example, try to go down the slope instead. So there is a serviceability issue with drainage design. You're not going to have a drain that's eventually not going to be clogged up. So you have to ensure that you design these drainage systems with in mind that they can get clogged up. So that's the drainage system. Different applications of drains. As I mentioned, you can have a trench drain and you can place this on top of slopes. You can use this inside pavements so you don't build up pore pressures underneath, because if you have pore pressure and cyclic loading, this can reduce the effective stress underneath your pavement. We can also put retaining wall drains. So there can be an entire fill material behind here that's very pervious, meaning that we don't expect significant excess pore pressures to develop behind it. So this is an example of a drain. This pipe here is also an example of a drain. For dams, you can have very pervious components inside your dam to promote seepage through, so you don't build up excess pore pressures, suppress and control sporadic resurface of the water. Interceptor or toe drains is what we use for slopes as well. We often can install these at the crest or at the toe of a slope to control excess pore pressures. And the one we're most familiar with is the use of PVD drains to dissipate pore pressures for land reclamation. So these are applications of drainage. Advantages: drains are cheap, right? Disadvantages: well, they can get clogged, and you probably need to service them every now and then. Some drains cannot be serviced though, right? Once you put it in the ground, you can't really take it out unless you excavate the soil around it. So that's perhaps a disadvantage. Advantages, as we mentioned, cheap, and it can reduce all sorts of problems caused by excess pore pressures. Reduce lateral earth pressure, well, hydrostatic pressure. Reduce uplift. Reduce erosion, internal or superficial. You can even eliminate frost heat in northern regions, reduce moisture content. So drainage is definitely a ground improvement method, perhaps the simplest and the cheapest. If you can control water, we solve a lot of problems in geotechnical engineering. The next major groundwater control measure is dewatering. Now, for dewatering, we can put in pumps at different levels. It really depends on what your final groundwater level should be. If it's for a deep excavation, you probably need to sink pumps in on the passive side of your excavation. If you want to lower the groundwater outside your excavation, you probably need to use a combination of deep wells and lower wells, some pumps as well. So dewatering is perhaps, after drainage, the second easiest form of ground improvement. If we can lower groundwater table, then we can have drier conditions, less pore pressures to deal with, and improve soil conditions in terms of strength and stiffness. As I mentioned, dewatering is simple. You see a pump. The only problem with deep pumps is you have to drill a borehole, sink the pump in. Pumps malfunction all the time. They clog up as well. A lot of pumps, once you throw them in, deep pumps, you can't really get them back because they get stuck. It happens all the time. And dewatering wells wear down with time. So don't expect dewatering well to have the same output because it can get clogged and fine as well for pumps. So these are perhaps the advantages and limitations of dewatering. So I mentioned there are two types of main pumps we use in construction, particularly in Hong Kong. Some pumps are easy to deal with, right? What you do is you just dig a trench, you throw a pump in here, and you can draw down the groundwater table. So initially the groundwater table may be here. If you turn on a sump pump, then we can suppress the groundwater table like this. So something as simple as this is a very nice form of ground improvement. If you want to be more complex, then you can drill a borehole and sink a dewatering well inside. The charm of a well point is that you can go to much deeper in the ground, much deeper elevations. So if you need to have a deep excavation and need to suppress the groundwater table, then you can sink in several well points to try to suppress the groundwater table. This is very commonly used in Hong Kong. Sump pumps and well points. Sump pumps, we have effective suppression depths of probably 1.5 meters or less. Well points, well, it depends. If you have a lot of well points, you can probably have much better control over how your phreatic surface looks like in the ground. Sometimes well points may not be effective if you're adjacent to the sea as well. The recharge rate is much higher than the rate that you can take the water out of the ground. So bear that in mind. So these are the two main types of pumps we deal with in routine excavation for dewatering. For well points, you can use deep wells. Deep wells, you can have various types of pumps. You can have pneumatic pumps, you can have electric pumps. They function for the same purpose, but with deep wells, the application is likely for cofferdams, deep excavations, and for sump pumps, you're probably just looking at a temporary alleviation of the groundwater table so you can get some ground improvement done quickly. More often than not, if you don't need to sink deep wells, you probably won't because it's expensive to drill a borehole into the ground. So you can see this is a typical cross-section of a deep well. A deep well also needs a filter, right? Because once the fines get into your pump, then your pump will malfunction and cannot operate. So filtration is also used for deep wells as well. And you can see on this particular diagram how you can use, there's 4 pumps here to suppress the groundwater table. So outside the site, you probably have a groundwater table like this. If you turn on all 4 of these pumps, 1, 2, 3, 4, then you can probably get the groundwater table something like this. And more often than not, we've tried to get this to be about 1 meter below the formation level so that we can carry out construction inside. And the most dangerous thing with these types of deep wells is that they have to remain functional because we rely on them to protect whoever's working inside this excavation pit. On top of these pumps, you can also see that there are 2 diaphragm walls here. And we'll talk about diaphragm walls, cofferdams, pumping tests in our next class. And we'll try to tidy up this lecture and move to chemical means. So thank you for your time today. I'm sure our next class.